Good day, everyone. We are Team 6, and we would like to introduce our term project Deeper Hyperion. This work is an extension and replication of the paper Deep Hyperion, exploring the feature space of deep learning-based systems through elimination search. So first, let me introduce you the problem. So dependability of deep learning systems is now more crucial than ever because deep learning systems are now being used in many safety critical domains like autonomous driving, medical domains, and now the dependability has become very crucial. And so the million-dollar question here is, how do we ensure these systems can be trusted with diverse real-world inputs? Because in training, these systems have seen only very small parts of real-world inputs, and there can be cases where there are various real-world inputs that we haven't considered during training that can potentially break our systems. And traditionally, we have used code coverage metrics, but these are not effective because deep learning systems behavior changes depending on what type of data it was being trained on. As well, we now also have white box approaches, but these approaches are not sufficient to understand exactly which inputs are misbehaving, which inputs are causing misbehaviors. So it would be nice if we could see a detailed view of the system's behavior with very diverse inputs. And so the question is, what about a feature map? So what if we could see a feature map to interpret the system's behavior based on different inputs characteristics? So that is what Deep Hyperion does. So Deep Hyperion is an automated test input generator for deep learning systems, and it generates diverse set of high performing test inputs. And here high performing means test inputs that can potentially cause errors within the systems, or meaning these high performing inputs can cause the system to misbehavior, close to misbehavior, or to misclassify. And Deep Hyperion illuminates the input space by returning the highest performing solution, and the user is able to define what search space they want. And Deep Hyperion then finally provides a feature map where inputs are positioned based on their characteristics, and then the user can understand which inputs expose which misbehaviors. So for example, in this figure, this is a handwriting, and we have in our space, we have two features, which are boldness and discontinuity. And so depending on what the values of these features are, Deep Hyperion can help us understand where exactly does your model break. So here, the red circles, the handwritings under the red circles show inputs that are misclassified or very close to being misclassified.
Okay, so we first do the replication on the original work. The results on the misbehaviors found by the Deep Hyperion, the Deep Janus, and DL Falls on demonstrated the qualities of the distinct improper behaviors identified by each tool within the MNIST system and their distribution sparsity on the map. The Deep Hyperion detected over 100 distinct error behaviors for each feature combination, outperforming other tools by generating a more diverse array of faults. Deep Hyperion is capable of exposing a substantial number of misbehaviors, and more importantly, reveals a highly diverse array of misbehaviors associated with distantly related feature combinations. The results displayed the number of field map cells and their sparsity produced by each tool for the MNIST system. Deep Hyperion covered all feature maps more extensively than other tools, with large effect sizes and p-values consistently below 0.05. The color intensity of the cells within the feature map represented the average misbehavior probability. We call it MP during runtime. I guess it's we set it as a 3,600 as a paper set. For the corresponding feature combinations, with darker colors indicating higher probabilities, and explored combinations by the Deep Hyperion were denoted as blank cells. The study highlighted the cells with MP that is bigger than 0.8 and a lower confidence interval boundary that is bigger than 0.65 with a dark border, indicating a high likelihood of inducing misbehavior whenever inputs were placed within these cells. For the extension of the experiment to the MNIST dataset, we employed the same setup. Actually, the fashion MNIST, I think everybody knows about that. It's a data set of the Zalando's article images consisting of a training set for 60K examples and a test set for 10K examples. With each example being a 28 multiplied by 28 grayscale image associated with one of the 10 classes, just like the MNIST did. The analysis highlighted the deep Hyperion's adaptability to the dataset. In addition to the analysis similar to those performed on the MNIST, it is noteworthy that the F-MNIST dataset actually contains more complex image context with a richer set of the feature, such as the texture, styles, and the types of the clothing. The testing particularly focused on tools capable of reviewing misbehaviors highly associated with fashion style and the designs. So first, the misbehavior probability analysis. F-MNIST model seems to exhibit a broader range and a higher possibility of the misbehaviors across the feature space. By the way, the F-MNIST always occur in the right side. I mean, the right picture, the right figure is the MNIST, and the left is the MNIST. So in this way, which may be attributed to the higher complexity of the dataset, the MNIST model shows a tighter clustering of the misbehaviors with a fewer high possibility outliers, suggesting a more consistent performance across the feature combinations, but still with specific areas of vulnerability. So the second analysis detail is about the collisions and misbehaviors analysis. The model tested by the F-MNIST dataset appears to have more frequent and diverse misbehaviors compared to the MNIST model, as the original paper did, which could be due to the complexity and variety of the feature present in the F-MNIST images. This insight could be useful for improving the robustness of the model by targeting the specific areas of the weakness. And the third, for the heat map bitmap orientation analysis, in conclusion, by comparison, while both datasets exhibit variations across the bitmap and orientation combinations, the F-MNIST heat map shows a greater intensity of the extremes, indicating more significant performance deviations. This suggests that the model may require more like better tuning ability to handle the complexity of the F-MNIST dataset efficiently. Conversely, the MNIST heat map indicates a less dramatic range of the performance differences, which might be expected given the relevant simplicity of the dataset itself.
As the second extension, we worked on a multimodal deep Hyperion. The original work aimed at eliminating the map of failing or near failing test cases. Then we thought that it would also be feasible to eliminate a map of test cases inducing different behavior among multiple models. And we adopted baseline models, one from the original paper, and trained a simple CNN-based classifier. Now, we need a new fitness function that could achieve our goal. If two predictors give out the same class, calculate the sum of activation differences. And if they show a different behavior, we set it as minus 0.1, just like the original fitness. This is our resulting fitness. At this point, you may wonder that our objective is counterintuitive. Why not maximizing, but minimizing the activation difference? We conjectured that above setup can generate inputs that could cause different behavior unexpectedly, thus more valuable. And actually, it did. We'll look at the experiment results. Just like
the FMNIST case, we put results from the original version on the left side and new version on the right side. And I'll basically focus on the right side. Let's take a look. This heat map represents the likelihood of different behaviors when the system's internal activations are altered minimally, but such that they still cause a different output behavior. The goal here is to understand the system's sensitivity to small perturbations. Darker squares indicate higher probabilities of different behavior under these conditions. The presence of these darker squares suggests that there are specific areas within the feature space where minimal changes can lead to misclassification or other errors. Next, collisions and different behaviors. As you can see from the right figure, it is darker and contains more spots. So basically, this one also supports the same ideas. This map likely has a higher concentration of collisions or different behaviors in particular areas, indicating that input images with certain orientations or bitmaps are especially brittle. Finally, fitness heat map. The red dots indicate inputs giving near zero yet positive fitness. This means that both models result in similar activations among most classes. So the prevalence of red dots means that two models work identically in general. At the same time, these dark areas pop up as a possible danger zone. So to conclude, our work is more useful for pinpointing precise weaknesses in the model and areas where even small changes can compromise performance. Meanwhile, the original work offers a broader picture of the model's performance across different inputs. So, to achieve the best robustness, we argue that using both versions can contribute significantly.
So, as for the conclusion, we can say we have successfully replicated the deep Hyperion MNIST experiments, and we also expand upon MNIST to FMNIST. And FMNIST contains more complex and higher detailed examples, which we hope provides more insights to our deep Hyperion and how it works. And we also expand upon deep Hyperion framework to consider differential behavior, which we hope is useful for pinpointing precise weaknesses in the subject model. As for the future work, we hope to modify the fitness function. As Hyunjin mentioned, the current function is kind of counterintuitive, so maybe a different function may provide different insights. And we also want to investigate and compare with quantized models. So actually, before the proposal presentation, we wanted to work with quantized models. So we hope to still work with it with deep Hyperion, and hopefully we can gain new insights on where exactly quantized model break compared to larger non-quantized models. And we also hope to implement deep Hyperion with newer deep learning frameworks. So because current implementations are based on TensorFlow 1.3 or less, we hope with newer versions we get higher efficient deep Hyperion. Thank you.